Today, I'll be finding a way to find like an area of something like this using polar coordinates, where if we have some theta 1 to some theta 2, we can find the area in between theta 1 and theta 2 if we're given the polar function and theta 1 and theta 2. Now first, we need to define what an integral is. So what is the integral of f of x dx? Well, if f of x is something like this, or if this is the graph of f of x, where y equal f of x, then the integral of fx would be the area under the curve, right? So it would be the sum of multiple rectangles, like this. So it would be f of dx times dx plus f of 2 dx times dx plus f of 3 dx times dx, and so forth, where dx represents the base of each rectangle and f of dx represents the height. So this first rectangle here would have a height of f dx and a base of dx. The second rectangle would have a height of f of 2 dx because its position is 2 dx. This is 2 dx, this is 3 dx, this is 4 dx. Hence the height here would be f of 2 dx, this would be f of 3 dx, and this would be f of 4 dx. And dx, we're keeping dx constant. It would be the base of each of these rectangles, and we're making dx approach 0, so our approximation becomes more and more precise, and hence we get an integral. So this is the definition of an integral. So f of dx equals that. Now, I'm going to pose you a question. How do you find the area of this section of a circle? How do we find the area of that? Well, the full area of a circle is just pi r squared, but that only gives us the area of the full circle. So if we're given theta in radian mode, what area is this section? Well, the area of this section would merely be theta over 2 pi times pi r squared, where pi r squared is the full circle and theta over 2 pi is the portion of the circle. Because when theta equals 2 pi, this just becomes 2 pi over 2 pi times pi r squared, and hence becomes pi r squared, because 2 pi is the full circle. If we're looking at a unit circle, 2 pi would go like this. However, if theta was merely pi, it would only be half of the circle. It would be, if we look at a unit circle, it would go from here to here, and this is pi. So hence if we plug in here, pi 2 pi times pi r squared, we'd only get pi r squared over 2, which is half of the area of the circle. Hence, this theta over 2 pi times pi r squared equation works out, where theta over 2 pi is the portion of the circle and pi r squared is the full area of the circle. Now, with polar equations, we split up the sections of the area in a different way. We can think of something weird looking as this, as composed of many pizza slices. So let's start from here. So we can think of this as this one pizza slice here. If we go here, this would be another pizza slice. And here, this would be a third pizza slice, and so forth. We can think of it as many pizza slices. And so what would be the area of, okay, let me just draw a pizza slice here. What would be the area of this pizza slice? And by the way, this pizza slice can also be considered a portion of the circle. So what is the area of this pizza slice? Well, as we found before, the area of a single pizza slice is merely theta over 2 pi times pi r squared. And we're thinking of this weird shape here as composed of many parts of a circle. So hence, this one pizza slice would have an area of theta over 2 pi times pi r squared. Now, how do we sum all these pizza slices? We want an integral. Well, we can sum it by making theta approach 0, so our approximation becomes very, very, very precise. So let's do that. So if we sum in, we make theta approach to d theta. Oh, by the way, this just equals, we can cancel out the pi's, we get theta over r squared times 2. And by the way, r is also a function of theta. So what we can do here is, so let's make this first portion, well, let's call like from here to here would be some d theta, and from here to here is also some d theta. By the way, my drawing is not exact, so it would be something like this. D theta, and by the way, r is a function of theta. D theta times r theta squared. That would be the area of this first pizza slice here. And the area of the second pizza slice would be d theta times r2 theta, or rd theta, and 2d theta squared over 2. The third pizza slice would be d theta times r3d theta squared over 2, and so forth. Now let's factor some things out. We can factor the half out, and that's about it. We factor the half out. 1/2, and we get this. I'm gonna put the d theta in front, or no, to the right. So we get this, r d theta squared times d theta plus r2d theta squared times d theta, and so forth. But what was our definition of an integral? Our definition of an integral was f of x dx just equals f of dx times dx plus f of 2dx times dx, and so forth. And this looks really similar to this, except that this just has a 1/2, and each f of x term is squared. But if we square f of x squared dx, it would just simply equal f of dx squared times dx plus f of 2dx squared times dx. So the squaring is not really a problem. So if we factor out 1/2, this would merely equal, if we change our f's to r's and x's to thetas, we would get this. The integral of r theta squared d theta equals r d theta squared d theta plus r 2d theta squared d theta dot dot dot. And hence the integral from, like, say, from some theta 1 to some theta 2 would be theta 1 theta 2 r theta squared d theta, and this would be an integral from theta 1 to theta 2 for a polar coordinate. Let that sink in. Oh, whoops, I forgot the half. So we need to apply 1/2 here, and there needs to be a half here too. So let that sink in. Theta 1 to theta 2, there's a 1/2. And that's where the 1/2 comes from. Now I'm going to explain to you why we can't think of a polar coordinate as made up of multiple rectangles, and why we had to think of it as composed of many pizza slices. If we think of it as many rectangles, here's what would happen. We get this rectangle, we get this rectangle, and we get this rectangle, and so forth. We can't think of it like this because the rectangles overlap, and however small we make dx to be, if we make dx too small, look what would happen. The overlapping would be negligible, yes, but like, so much area is not covered. This area is not covered, and while if we make the rectangles too big, too much area would be overlapped, but we would cover more area. So rectangles would not give us an accurate representation. We have to use pizza slices because the pizza slices don't really, fight with each other. They don't fight for space. They're just there. And that's why we think of anything on a polar coordinate as made up of multiple pizza slices, or made up of multiple circles. And hence why we use the partition of a circle to find an integral for polar coordinates. And thank you for your time. Bye.